In this mini-lesson, we continue our discussion of FreeFall begun in the last mini-lesson. But now, instead of confining our attention to motion in one dimension, we will consider FreeFall in two dimensions. First, however, let's take a brief digression to review how the concepts of kinematics, position, velocity, and acceleration, generalize to two or three dimensions. In 1D, the position of an object is given by a signed number, which represents where the object is along the line relative to the origin. In 2D, you need two signed numbers, x and y, the object's coordinates in the plane. So position goes from being a number in 1D to being a vector in 2D and 3D. The components of the position vector r are the coordinates x and y. A brief comment on notation. While it's most common to denote a vector by a symbol with an arrow over it, in print it's also common to denote a vector by a boldface symbol, as is done with the position vector here. Velocity also becomes a vector in 2D and 3D. As always, velocity measures the rate at which position changes with time. But now both the x and y components of position can change with time. So the components of the velocity vector, v, are v sub s equals dx by dt, and v sub y equals dy by dt. The direction of the velocity vector is the direction of the object's motion, and the magnitude of the velocity vector is the object's speed. Not surprisingly at this point, acceleration is also a vector in 2D and 3D. As before, acceleration measures the rate at which velocity changes with time. But now, both the x and y components of velocity can change with time. So the components of the acceleration vector, a, are a sub x, which equals dv sub x by dt, which in turn equals the second derivative of x with respect to time, and a sub y, which equals the derivative of v sub y with respect to t, or equivalently the second derivative of position with respect to time. The acceleration vector is non-zero if either the object's speed or direction of motion, or both, changes. That's because the velocity vector includes both the speed and the direction of motion. So if either of these changes, the velocity changes, which means the acceleration is non-zero. If you resolve the acceleration vector into components parallel and perpendicular to the velocity vector, as shown in the figure below, then the component parallel or antiparallel causes the object to speed up or slow down, and the component perpendicular causes the object to change its direction of motion. Okay, now that we've reviewed the meaning of kinematic concepts in 2D, let's see how motion at constant acceleration works in 2D. FreeFall in 2D is then just a special case. Suppose the acceleration of an object moving in 2D is constant. That means both the x and y components of the vector A are constant. How does the fact that the motion is in 2D affect our previous constant acceleration equations? The answer is not at all. Actually, you get two sets of constant acceleration equations, one for the x part of the motion and one for the y part, as shown here. Notice that the only thing linking the x motion equations with the y motion equations is time. Of course, it wouldn't make sense for the time to be different for the x and y motions, since x and y refer to the coordinates of one object. But what's perhaps a bit surprising at first is the fact that the x and y parts of the motion evolve in time completely independently of each other. This means that we can solve for the x and y motion of the object as if they were two separate constant acceleration problems, linked only by common initial and final times, because that's really what they are. We'll see how useful this approach is in solving 2D constant acceleration problems, and particularly the motion of projectiles. Suppose an object in free fall has both vertical and horizontal motion, so that it moves in a vertical plane. The prototypical example of this is a projectile, such as an arrow, a cannonball, a bullet, a baseball, and so on. For this reason, free fall in 2 dimensions is often called projectile motion, and I'll use the two interchangeably. Since the object is in free fall, the only thing affecting its motion is gravity by definition. And so its acceleration is a constant 9.8 meters per second squared vertically downward. As we see, projectile motion is a specific case of constant acceleration motion in 2D, with a sub x equal to 0 and a sub y equal to minus g, or minus 9.8 meters per second squared. Note that we have assumed up is the positive y direction. Plugging this acceleration into the 2D constant acceleration equations gives these equations for projectile motion, or free fall in 2D. Notice that the horizontal velocity is constant. Its initial and final values are the same. That's what it means for there to be no acceleration in the horizontal direction. The horizontal velocity is just constant. So, as we see, the evolution in time of the object's horizontal position is just what you would expect for an object that's moving at constant velocity. Not so for the vertical part of the motion, because there is a non-zero acceleration in the vertical direction. The vertical motion is just ordinary constant acceleration motion. Let's do an example to see how this all works. A criminal is escaping across a rooftop and runs off horizontally, landing on the roof of an adjacent building. The horizontal distance between the two buildings is 3.4 meters, and the roof of the adjacent building is 2.0 meters below the jumping off point. Part A asks, what would be the minimum speed needed by the criminal as he runs off the roof? And Part B, if this were his initial speed, what would his speed be just as he lands on the roof of the adjacent building? Let's draw a picture of the scenario. Here we show the criminal running off the edge of the taller building, and here is the path he follows through the air to land on the shorter adjacent building. The minimum speed he needs would be the speed that allows him to land just at the edge of the second building, with no room to spare. So that means his horizontal displacement is exactly 3.4 meters, the spacing between the two buildings. Had he been running faster, he would have landed further on the second roof, and the horizontal distance would be greater than 3.4 meters. The free fall happens between two events. The initial event is when the criminal runs off the rooftop of the first building, and the final event is when the criminal lands at the edge of the rooftop of the second building. Let's tabulate what we can glean about the kinematic variables from the information given in the problem. First, let's choose the origin of both time and coordinates to be at the initial event, as usual. That means t sub naught, x sub naught, and y sub naught are all 0. Since the criminal is in free fall between the two events, his acceleration components are a sub x equals 0 and a sub y equals minus g. Since he lands just at the edge of the second building, his final position is x sub f equals 3.4 meters and y sub f equals minus 2.0 meters. The minus sign on y sub f is because the ending point is below the starting point, which we've chosen to be the origin. Since we're told that the criminal runs horizontally off the building, the initial velocity vector must be horizontal. That means the y component of the initial velocity is 0. The initial velocity is all horizontal. We don't know how fast the initial velocity is, but we do know that whatever it is, the x component of the final velocity will be the same. Since there is no horizontal acceleration, the horizontal velocity doesn't change. The vertical velocity does change, however. We don't know what the y component of the final velocity is yet, but we do know that it should be negative. Finally, we know nothing yet about the final time. We have three unknowns to compute: v naught sub x, which is the same as v final sub x, v final sub y, and t final. Let's start to solve for them. Since we know t naught, y naught, yf, and v sub naught y, and a sub y, we can use the first constant acceleration equation for the y motion to compute t sub f. In particular, t sub naught, y sub naught, and v sub naught y are all 0. So this equation simplifies to y sub f equals minus 1/2 g t sub final squared. Solving for t sub f and plugging in numbers gives t sub f equals 0.64 seconds. Now that we know t sub f, we can use the first constant acceleration equation for the x motion to compute v sub naught x. And since t sub naught, x sub naught, and particularly a sub x are all 0, this equation also simplifies considerably. X sub f equals v naught x times t sub f. Solving for v naught x and plugging in numbers gives v naught x equals 5.3 meters per second. Incidentally, this means that v sub fx also equals 5.3 meters per second, since the horizontal velocity doesn't change. And finally, we can use the second constant acceleration equation for the y motion to compute v sub final y. Here, t naught and v naught y are both 0, so that v sub final y equals minus g times t sub final. Plugging in numbers gives v final sub y equals negative 6.3 meters per second. And as predicted, the final velocity's y component is indeed negative. Now we are ready to replace the question marks in our table of kinematic variables. From v naught x and v naught y, we can compute the final speed of the criminal just as he lands on the second building. From the Pythagorean theorem, we find the magnitude of the final velocity, or the final speed, to be 8.2 meters per second. And finally, we're ready to answer the questions in the problem. What would be the minimum speed needed by the criminal as he runs off the roof? Well, that's just v naught x, which we found to be 5.3 meters per second. And if this were his initial speed, what would be his speed just as he lands on the roof of the adjacent building? Well, that's just v sub f, the magnitude of the final velocity vector, which we found on the last slide to be 8.2 meters per second. That's it for this mini-lesson. In the next mini-lesson, we'll work through another example of projectile motion to see some different issues one can encounter in these kinds of problems.